Okay, so today what we're going to do is we're going to do a couple more examples with weak acids and weak bases. Now, our first one that we're going to look at says, what is the pH and percent of ionization of a 0.0037 molar solution of carbonic acid, H2CO3? Now, since carbonic acid actually has two hydrogens in it, it has two acid dissociation constants, K of A1, K of A2, one for each of the hydrogens that it can release. So just like what we saw with yesterday, we have to set up a reaction in which we are losing a hydrogen. So H2CO3 aqueous equilibrium, get our hydrogen ion plus hydrogen carbonate. Then we have to set up our ice table. So let's start setting some things up. So we have our initial concentration of carbonic acid, 0.0037 molar, hydrogen and hydrogen carbonate. So it's going to be 0. Change, negative x, 0.0037 minus x, and x. So that's what our ice table looks at. Now, since we are losing our first hydrogen ion, we're going to use the K of A1. So K of A1 is equal to hydrogen ion concentration times hydrogen carbonate all over H2CO3. 4.3 times 10 to the negative 7th is equal to x times x all over 0.0037 minus x. And just like what I said yesterday, if our K of A is really small, so we're looking, the times 10 negative third, negative second, negative first. Those numbers would be big enough for the change to really come into play. Negative fourth and so on and so forth. Negative fifth, negative sixth, negative seventh. Those numbers are so small that we're not going to really worry about the change. So since our K of A is times 10 to the negative seventh, we can negate out that minus x. X squared is equal to 0.0037 times 4.3 times 10 to the negative 7th. And let's just see what that comes out to be. 0.0037 times 4.3 times 10 to the negative 7th. Okay, so x squared is equal to 1.59 times 10 to the negative 9th. So x would equal to the square root of 1.59 times 10 to the negative 9th. Trying to find the square root. Yeah. Alright, so x is equal to 3.99 times 10 to the negative 5th molar. So that is for our hydrogen ion. Okay. So hydrogen ion is equal to 3.99 times 10 to the negative 5th molar. Now, since we do have the second hydrogen in there, we could possibly set up another dissociation so we break apart that hydrogen from the hydrogen carbonate, get the hydrogen ion and a carbonate ion. But since our dissociation constants are pretty far apart, and the thing is, if K of A are a difference of 10 to the third, we don't really need to set up another ice table for dissociation, because since this is such a small number, we're not going to really see a really big change in the hydrogen ion concentration if we try to break apart that other one. So for this one, we have our hydrogen ion concentration, we can find our pH. So pH is equal to negative log of 3.99 times 10 to the negative 5th 3.99 times 10 to the negative fifth. And I'm coming up with pH of 4.40. And for the percent ionization, we're going to take our hydrogen ion concentration at equilibrium over our weak acids concentration initially times 100. 3.99 times 10 to the negative fifth molar over 0.0037 molar times 100. 3.99 times 10 to the negative fifth divided by 0.0037 times 100. And our percent of ionization is 1.08%. Okay, so recap with this one. If the K of A's are a lot closer, less than 10 to the third, so less than 1,000 difference between the numbers, then we would have to set up another dissociation to actually figure out what the pH would honestly be. Or if we want to figure out what is the concentration of carbonate in this one, we'd have to set up another ice table. But if they are very far apart, we're not going to see much difference, so we don't have to really set up another dissociation reaction and set up another ice table. Alright, so let's look at a weak base. And this is kind of like what we did yesterday. So what is the pH of a 0.65 molar solution of pyridine, C5H5N, and we're given the Kb for pyridine to be 1.7 times 10 to the negative ninth. So for our weak bases, we take our weak base, we're going to add that with water. And if you kind of remember from the video from yesterday, the reason why we're going to add in water is so that we can get our hydroxide ion, because water is going to break apart into hydrogen ions and hydroxides. So the hydrogen ion from the water is going to attach to the pyridine. So we're going to put it as C5H5NH+. Then we're going to set up our ice table once again. Now, since water is a liquid, we can negate it out because at equilibrium, liquids and solids, their concentrations aren't going to change much. We'll have to worry about them. 0.65 molar, 0, 0, plus x, x, minus x, 0.65 minus x. So here's our equilibrium, or our nice table. 1.7 times 10 to the negative ninth is equal to x times x over 0.65 minus x. And just like what we talked about before, if we look at our Kb, 1.7 times 10 to the negative ninth. Pretty small number. So we're going to negate that minus x. X squared is going to be equal to 0.65 times 1.7 times 10 to the negative ninth. 0.65 times 1.7 times 10 to the negative ninth. Coming up with 1.11 times 10 to the negative ninth. So take the square root to find x. X is going to be equal to 3.32 times 10 to the negative fifth. Okay. So x is equal to our hydroxide ion concentration. So to find the pH, we can, like I said, we can take two different routes. Usually most people take, find the pOH, so negative log of 3.32 times 10 to the negative fifth. I'm coming up with 4.49. Then to find the pH, we take 14 minus the pOH, 14 minus 4.49. 14 minus 4.49. And we come up with 9.51 for an answer. Now, how are K of A and K of B relevant to one another? Well, if we took the K of A of a compound and multiplied by the K of B, if we were able to find that, that'd equal to the K of W. Since acids and bases are the opposite of one another, if we put them together, they should neutralize one another to a certain point. Okay, so I kind of hope this has helped out. If you have any questions, please email me, and I will talk to you later. Thank you.